You're welcome to the sixth session of Business Mathematics. Today we are looking at mathematical modeling. The objective of this session is that at the end, you should be able to understand what decision variables are, what is the objective function of the model, what are the linear constraints, i.e. linear equations or linear inequalities, and then how to formulate these word problems using the decision variables, objective functions, and the linear constraints. I'll be explaining further. A business mathematical model is a mathematical representation of a real world problem or word problems, right? So we are just representing word problems or business problems in a mathematical form, right? We're going to represent it in mathematical form. Word problems require translating a real world scenario into mathematical expressions and equations to find a solution, right? So we have a word problem, right? That is a real world scenario problem. And then you're just going to input it or just represent it in a mathematical form just to find a solution to these word problems, right? So example is that for a business problem, uh, amenable to mathematical representation, right? A mathematical equivalent or formulation of the problem enables analysis than the worded equivalence due to its clear and concise form of the representation. The first step of a mathematical formulation. So, how do you formulate these business problems and then make it easier for us to find a solution, right, in a mathematical way? So, the first step is to of any mathematical formulation is the definition of what is called decision variables, right? What are the things that you are finding for? What are you looking for? Are you looking for the number of bags or number of number of bags that you produce for the cocoa farm, right? Say you have a farm and then you want to know the number of bags to be produced or to produce for say yam, right? You have that of yam and that of cassava, that of plantain, right? So these let's say crops are going to be represented with what is called decision variables, right? To indicate the items or the crops in question, right? That is decision variables. And then on our next slide here, we have a practical example to explain or show us how to deal with these word problems and then how to formulate them, right? So the first step is the decision variable, and I will say that an example is here to help us understand. Imagine you have 10,000 Ghana cedis to invest in two assets. So here you have two assets, and then you have 10,000 Ghana cedis to invest in it. Your concern is how much to invest in asset one and asset two, right? It could be anything depending on the information at hand, right? So for instance, having the 100,000, the 10,000 Ghana cedis, you could decide to put just 1,000 Ghana cedis in asset one and 9,000 Ghana cedis in asset two. You could also, depending on the information, decide to put 6,000 Ghana cedis in asset one and 4,000 Ghana cedis in asset two. The number of ways of a division could be endless, right? Assuming no other information exists, you could decide to invest 50-50, that is 5,000 each in these assets, right? So instead of thinking of all possible allocations, we will rather let x1, see, x1 here is a decision variable, represent or be a variable representing the amount of money to be invested in asset one, right? And x2 represents the amount of money to be invested in asset two. That is how to go about the decision variables. You want to know how much you want to invest in each of these assets. So we represent these amount of money to be invested in each of these assets with what is called decision variables, i.e. x1, x2, x3, x4, depending on the number of assets you have to invest in, right? So then we'll say that x1, which is the amount of money to be represented in asset one, right? And plus x2, which is the amount of money that is going to be invested in asset 2 should be less than or equal to the total amount of 10,000 Ghana cedis. That means the amount of money you invest in asset 1 and asset 2, the summation of that shouldn't exceed the amount that you have available, right? So it means that you have 10,000 Ghana cedis available. So what you're investing in these two assets should rather be equal to or less than this amount over here. So the symbol less than or equal to reflects that it is possible less than 10,000 Ghana cedis could be invested in the two assets, right? You can't exceed the available resource because you just have 10,000, right? So now let's take this practical example here that will help us to understand the formulation into details. The company manufactures products A and B using machine 1 and 2. Suppose machine 1 is available, that is what you have available. Total number of hours you have available for production, let's say, is 60 hours per week, i.e. for machine 1. Machine 2 is available 80 hours per week, right? In addition, to produce a unit of product A would require 2 hours on machine 1, right? And 4 hours on machine 2. Whereas a unit of product B would require 1 hour on machine 1 and 2 hours on machine 2. Right? In a problem such as this, the challenge is to decide how many of product A and product B to produce, taking into consideration the limitations, or what we call the constraints, the linear constraints on the availability of machine 1 and machine 2. So the production of these products A and B is dependent on the limitations. That is the linear constraints, right? The constraint that you have. Right? Do you have, if it's production of crops like this, right? Do you have land? What is the limitation on that, right? The labor, capital, looking at these are all constraints or limitations. Could be land, could be labor, could be capital, could be, say, agri offices, and even the crops as well. Let's say if you are into crop production, right? So here, this is how to deal with this. Let XA, that is decision variables here, let XA representing the decision variable for product A and XB decision variable for product B be the variable representing the number of units of product A to produce and product B respectively to produce per week. I hope you can see that. So whatever the unit of product A and unit of product B are, the total number of hours spent on machine 1 right here in the question cannot exceed 60 hours per week, because the question says that suppose machine 1 is available. What you have available, you can't go beyond what you have, right? That is available resource that you have with respect to the labor, let's say hours per week, right? Or the labor hours. It is 60 hours. So it is less than or equal to, so it cannot exceed 60 hours per week. And the total hours on machine 2 cannot also exceed 80 hours per week, right? So machine 2 is available 80 hours per week. Now, using the defined variables, a mathematical model or formulation for these limitations could be written as this. Say, alternatively, we could say that here we were told machine 1 is available 60 hours per week. That's what we have here. So it's less than or equal to 60 hours. This is another ideal way of writing it easily. 60 hours here machine here, when you refer, I say that machine 2 is available 80 hours per week. So I'll say this one is for machine 2, which I'll say it is less than or equal to 80 hours. Right. In addition, to produce a unit of machine A, sorry, product A, will require 2 hours on machine 1. 2 hours on machine 1, which is what? 60 hours per week. So 2 hours. So I'll say 2xa here, right? And 4 hours on machine 2. Remember, machine 2 has to do with the 80 hours, machine 1 has to do with the 60 hours. So if they say that in addition, sorry, the to produce a unit of product A will require 2 hours on machine 1. Remember, machine 1 is here 60 hours. So I'll say 2xa because say product A. And 4 hours on machine 2. So this is machine 2, also 80 hours. So I'll say 4xa because it says product A. Whereas a unit of product B would require 1 hour on machine 1. So I would say plus 1xb, or you can say just xb because it says machine 1. And 2 hours on machine 2. So I'll say machine 2 is here with available resource of less than or equal to 80. So I'll say plus 2xb. Right. That is how you illustrate this in a mathematical way. That's the decision variable, how you are going to represent them. Right. So this is the model based on the question we have here. Right. Okay. So after defining the necessary variables, right, the other information regarding the worded problem statement would then be translated into its equivalent mathematical form with the help of decision variables, right? The representation of the variables in the above example, right? This is generally accomplished using a combination of equations, inequalities, and functions. For this course, we will limit ourselves to only linear equations. So it could be linear equations that is representing the right hand side of our constraints, right? Right hand side of our constraints. It could be linear equations, it could be linear inequalities, it could be linear or multilinear functions. So here we represent the resources or what you have available with equal to based on the statement less than, greater than, less than or equal to, greater than or equal to at the right hand side of the constraint or left hand side in the linear equations and the linear inequalities, right? So based on the restrictions or linear constraints or the limitations, right? That's where we use these signs or symbols, right? So here on the next slide, we'll have what is called a linear equation. So linear equation is of the form this here, where AI is the coefficient or the parameter, B is the parameter that is of real numbers or constant term, and then xi is a variable. Linear equations are one of the tools used in translating a worded problem into a mathematical form for analysis. So example here, a company earns a before tax of 100,000 Ghana cedis. It has agreed to contribute 10% of its after tax profits to Red Cross Relief Fund. It must pay a regional tax of 5% of its profits, that is after the Red Cross donation, and a state tax of 40% of its profits after the Red Cross donation and regional tax. How much does the company pay in regional tax, state tax, and Red Cross donation? Right. So this question over here, this is how it is being represented mathematically or being formulated to find the required what the question requires us to, right? So to answer this question, we'll first translate the worded problem into an equivalent mathematical form. Step 0 is to define the decision variables, right? Identify the decision variables. So let R and S be the variables representing the amounts paid for original tax and state tax, respectively. Also, let's see represent the contribution to Red Cross. So the step one is to get your after tax profit. You say that after tax profit is your 100,000 here minus the state tax minus the regional tax, right? And the contribution is equal to 10% of the after tax profit. Regional tax is 0.05% of its after tax of its profits after the Red Cross donation. That is what we have here. And the state tax is 40% of its profits after the Red Cross donation and regional tax. Red Cross donation and regional tax. Regional tax is 5% of its profits. That is after tax after the Red Cross donation. Sorry. So that is what we have here. Just represented mathematically. So after tax is 100,000 minus your state tax plus the regional tax. That of the contribution is 10% of the after tax profit to the Red Cross donation, right? That's what we have here mathematically, and then this is 5%. This is okay. So right. So step one in solving this you have here is to substitute the function or equation of C into the R function, which has C, right? So we substitute that of C here, right, into which one? Into R here, which is having the C. So in place of this C here in the R function, you're going to represent it with this. That's the first step, right? So here it will be the 0.05 into bracket 100,000 minus the whole of this here, right? So then you will get this 0.995R is equal to 4,500 plus that of this. So the step 3 is to make S the subject, and then you have S to be equal to this, which is your fourth equation, right? Then you substitute the value or function of S in the state tax function, which is here, right, into the equation you have here. Then what you do is that you have expressed in R and C the equation that you have, right? So you just put, you see here it is S is equal to 199R minus 900,000, right? And then you are going to substitute the function of the state tax, which is 0.4 into brackets 100,000 minus the contribution to Red Cross minus the regional tax into this function you have here, right? Then simultaneously using equation 3 here and equation 4 here, you can find the answers to how much the company pay to regional tax, state tax, and then Red Cross donation. You can try your hands on this by when you get to this point, you just use simultaneous equation, either elimination or substitution to solve this, and then you get the answers correct. So the three linear equations together does represent the weather problem above, right? There are three equations and three unknown variables. That is the contribution to Red Cross, the regional tax, and then the state tax. Solving the three equations simultaneously leads to an amount to be paid to the state tax here 35,736.680. That to be paid to the regional tax is 4,702.194, and then the contribution to Red Cross is 5,956.113, right? That is what you get after solving this equation simultaneously, right? Let's go ahead here. The Smiths company would like to know the total sales units that are required for company to earn a profit of 150,000 if the units selling price is this, right? And the profit is this. The variable cost is 25 cedis. and the total fixed cost is 500,000 Ghana cedis. Right. Step 0 is to write the decision variable. So let Q be the variable representing the number of sales units to achieve a profit of 100,000. And what is profit? You know that profit is total revenue minus your total cost. And here from the function over here, total revenue is the unit selling price by the sales unit. Or say total revenue is price times quantity, right? That is 50 here by the quantity Q will give us 50Q. Total cost is also equal to total variable cost plus the total fixed cost. Here we have the total fixed cost of 500,000 plus total variable cost here 25. But total variable cost here is variable cost times quantity. That's why I have a fixed cost of 500,000 plus a variable cost of 25Q. So here we just find this using a mathematical expression. So profit is equal to 50Q minus this, right? We want to achieve a profit of 150,000. We must have 150,000, which is the profit, being equal to this. And that will give us the quantity or the sales unit. Then we can solve for Q that results in 150,000 profits. So doing your grouping of like terms, I would say will give you 25Q is equal to 150,000, right? 150,000 minus the 500,000, and that should give you 650,000, right? And then you have Q to be 26,000. That's dividing both sides by 25 will give you Q to be 26,000. So this is 25Q will be equal to 150,000 plus 500,000. That will give you 650,000. Dividing both sides by 25 gives us the 26,000, right? So the number of required sales units is 66,000 units to be able to get a profit of 150,000, right? Another example here, the XYZ manufacturing company has a total fixed cost of 1,200, a variable cost per unit of 2 Ghana cedis, and a total revenue function for selling Q units of a product as 100 root of Q. Determine the break-even quantity of XYZ manufacturing company, right? What should be the quantity if the profit of Ghana cedi 150,000 is desired? At break-even, we know that total revenue is equal to total cost. And then we let Q represent the quantity that we are looking for, right? So we say that total cost is equal to total fixed cost plus total variable cost. And the total cost is total fixed cost is 1,200 here, plus the variable cost is 2 times the quantity that will give us 2Q. Revenue has been given already as 100 root of Q, right? So here on our next slide, we have at the break-even point, total revenue equals total cost. That's what we had as our total revenue, which is our total cost, or anyways, is fine, is 1,200 plus 2Q is equal to the revenue of 100 root of Q. So solving this, right, by grouping like terms and then using your square roots, or you can also use the quadratic formula to solve this function here, and then you are going to get the values of Q or quantities as 400 and 900. The maximum profit is achieved at quantity of either 400 units or 900 units. Now, to attain a profit of 150,000, total revenue minus total cost is equal to 1,000, right? So here we have the same function we have here, but the revenue function minus the cost function will give us the profit of 150,000. So we can also solve that. You can solve for Q to also attain the value for our quantity, right? To get the function or the value for Q, right? Right. So here we have the same idea about the linear constraints and the symbols to use. Here we have linear inequalities, could be of the form this, less than or equal to, greater than or equal to, where AI is the coefficient or parameter, and then B is the parameter of real numbers or constant terms. Xi is the variable, and the symbols are less than or equal to, greater than or equal to, right, respectively. So familiar words and their equivalent symbols. So based on the word, so in the word problem, you have these kind of words, and then you're going to represent them with these symbols, right? So at least, not less than, right, is greater than or equal to, at most is less than or equal to, or not more than, exactly, available, should be, must be. We use the equal to sign. A person wishes to invest 20,000 in two enterprises, right? So the total returns for the year would be at least 1,440, right? One enterprise pays 6% annually, the other has more risk and so pays 8% annually, right? How much should be invested in each, sorry, enterprise? Step one, your decision variable. So let X1 and X2 here represent the amount to be invested in enterprise 1 and enterprise 2 respectively. Step 2 is to write what is called the constraint, right? So these amount to be invested are subject to these linear constraints. So we say that the summation of the first enterprise and the second enterprise is equal to the 20,000 to be invested, right? That's the total amount. And then their returns, or what it pays annually, based on the enterprises. So we'd say that the total returns is at least, so we use greater than or equal to sign here. The first enterprise is 6% annually, so 0.06x1 plus second one is 8% annually plus 0.08x2, greater than or equal to 1,440, right? How much should be invested? So based on further solutions, we can find these values of x1 and x2, right? Okay, so this is how you can also go about it, just to find the amount to be invested in each of these enterprises, right? So based on this, you can make x2 the subject, and then you just substitute it to one of these equations here, and that will give you the amount to be invested in x1 and x2 respectively. Here we have x1 should be less than or equal to 8,000, and then x2 should be greater than or equal to 12,000 based on the final answers, right? Okay, so here the functions over here, that is the objective function. Remember this mathematical modeling or these word problems that we are representing in a mathematical form could take so many forms. What is the objective of the function or the word problem? Do you want to maximize profit or you want to minimize cost? Basically, that is the caveat we have here under mathematical modeling. It's either you are maximizing profit, right, or you are minimizing cost. The what we know as the basis of formulation of, let's say, a business, right? So in business, objectives are mostly modeled using functions. Notable business objective functions include the profit function, cost function, revenue function, time function, and distance. Right? Based on this can be what is called the objective function of the word problem. Right. Here we have a practical example to also help us. You can try your hands on this to enhance your understanding, right? Just take your time, read the word problem, identify the objective function, the decision variables, the linear constraints. If you're able to identify all these things, then you can solve this problem ideally, right? Right. Okay, so we have it here. Okay, so here, based on the question we have here, we would say that let's X1, X2, X3, and X4 be the amounts invested in the bonds, home loans, and auto loans. Right? These are my right? So based on what you are looking for. If it is 10, it will be X1 all the way to X10. Right? What is your objective function? Right? It's maximization of profit. So here you have 0. So bonds 0.1, 0.16, 0.13, 0.20. Right? That's the objective function. So then I'll write it X 0.1x1, 0.16x2, 0.13x3, 0.2x4. Right. So the constraints, what are the linear constraints or the restrictions or the limitations? You have it here, right? At present, 500,000 is available for investment in the bonds, home loans, and auto loans, right? Amount invested in personal loans cannot exceed the amount invested in. So what you have available is 500,000. You can write your first restriction. That of bonds, home loans, auto loans, and personal loans, right? Bonds, home loans, auto loans, and personal loans cannot exceed. So it's less than or equal to at present. Well, that's what you have available. It's less than or equal to 500,000. The next one is saying that here, if the amount invested in personal loans cannot exceed the amount invested in bonds. So here you should know the decision variables being represented with the decision, sorry, being represented with personal loans and the bonds, right? Then you can go ahead to do this. Minutes, please. Right. So the amount invested in personal loans cannot exceed that of bonds. So we just have it here as X4, which is that of personal loans, cannot exceed that of the bond. So it is less than this. And then same applies to the B. You write it not more than 10%, sorry, 25% of the total amount invested may be in personal loans. So here you have it here. Personal loans is X4 less than or equal to 0.25 of the total amount invested. The last thing to write on this formulation is what we call the non-negativity constraint, simply telling us that the amount being invested in this bond cannot be less than zero, right? You cannot invest negative to it 20,000 in bonds, home loans, auto loans. So this is always true. The decision variables you have should be greater than or equal to zero for all the decision variables. Right. The last part of the mathematical formulation is very important, since if we don't add this, we are implicitly assuming one can invest a negative amount, which is not true. So all the decision variables or what you are investing in should be greater than or equal to zero. Students will lose marks, a lot of marks. If you don't add this, it will go against you very much. So because it is very important, right? For the problems that seem obvious, negative amount is not possible. You can't invest negative 20,000 into treasury bills or any investment fund, right? So based on that, the final formulation will be this: our objective function, right? That's to maximize profit based on the annual returns. That is the objective function. The returns is going to maximize our profits. So it is subject to, so ST is subject to this constraint over here based on the amount available, the amounts invested in personal loans cannot exceed the amount invested in banks. B, the amount invested in home loans cannot also exceed invest. So that's what we've represented here on, I would say, 1, 2, 3 rows over here. And the last one is the non-negativity. So x1, x2, x3, x4 is greater than or equal to 0. You can write it that way, or this is also fine. Where ST stands for subject to linear constraint. That is, we want to achieve the objective of maximizing total annual returns, taking into account these restrictions or these limitations presented. This form of mathematical formulation where a linear objective is subject to a linear constraint is known as linear programming or linear optimization. So this mathematical model is also known as linear programming or linear optimization. And then our objective function is subject to all these linear constraints or restrictions. I hope you enjoyed this section. I'll urge you to take your time, go through this um, mathematical modeling session again, and you would be fine. I hope you enjoy this session. I would like you to like, share, and subscribe to this video, and then I'll see you in the subsequent videos as well. It's bye for now.